This is a supplementary video for the paper titled Panoramic Stereo Videos with a Single Camera. If you think of an omnidirectional image, it is essentially a 2D function I of theta phi, where theta and phi are the polar coordinates of the viewing angle. For an omnidirectional image, the center of the camera remains constant, and hence the whole image can be described as a 2D function. This 2D function could also be described in terms of a cylindrical projection where the parameters are theta and h, which are the horizontal looking angle and the vertical height. Several cameras have been proposed that can capture omnidirectional images. The point gray ladybug is a commercially available camera that uses 6 different cameras with their centers very close to each other. However, it would be an interesting idea if we can capture an omnidirectional image using a single camera. One such idea that has been proposed involves the use of catadioptrics, where you have a paraboloidal mirror and a convex lens that would direct the rays of light from the world to the camera in such a way that you can actually deflect all the rays of light from a panoramic image into a single sensor. Notice that this camera does not capture an omnidirectional image, however, it is a complete 360-degree panorama. Of course, commercial versions of this camera has been available in the market for some time now, and it captures images in a circular pattern which then needs to be de-warped to get the perspective view that one would like to have. However, if you want to capture omnidirectional stereo, the problem becomes far more difficult. The reason being, when you look around in different directions, the eyes of a person traverses the surface of a sphere. If you look forward, your eyes are on the left and right of the sphere. Let's assume that the eye location is denoted by theta I and phi I. If you're looking to the top right, then your eye position changes, and so does if you're looking at towards the left. Now, for each of those eye position, we actually see a different set of light rays that emanates from the world. This essentially means one would need to capture a different image for every possible eye location. This makes the problem of capturing omnidirectional stereo a problem of capturing a 4-dimensional function for theta I and phi I, as well as xi and xij and yij, which denote the pixels in the image. However, if you restrict your problem to panoramic stereo, not omnidirectional stereo, we would essentially restrict the motion of the eyes to that along a circle, a horizontal circle. This means your head is allowed to move only in the yaw and the pitch and not a roll. This significantly reduces the amount of information that needs to capture, and the light field one needs to capture reduces from a 4-dimensional function to now a 3-dimensional function, where theta denotes the looking angle along the horizontal direction and x and y denotes the pixels along the image. Now, the pixels that you see for the left eye and the right eye are different, and hence one could imagine that you have a series of cameras that would capture the left eye view along a circle and another series of cameras that capture the right eye view along the same circle, however in the opposite direction. Note that these two circles are in fact concentric. Now this makes the problem still difficult because now we need to capture a set of camera images that are moving along a circle and a second set of camera images which moves along the same circle but looking at the opposite direction, all at the same time without one camera occluding another. This is a very difficult problem to solve. Our problem now is to capture a three-dimensional light field function L of theta x y using image sensors that are essentially two-dimensional. Peleg et al. Has proposed a solution for this using a single camera that is rotated around a circle about a single axis. Multiple images from the camera is acquired during this rotation, corresponding to different viewing directions. Once the images are acquired, a set of small image strips are extracted from the left side of the image, which forms the views of your right eye, and a set of strips from the right side of the image forms the view corresponding to your left eye. Now all the strips for the left eye are stitched together to form a single panorama for your left eye, and the strips from the right eye are stitched together to form the right eye panorama. This also reduces the problem of representation. As we are storing individual panoramas for each eye, the problem of representation of a 3D function has reduced to now representing two 2D functions. A primary design idea is to use a slim mirror to deflect only the required strip of image onto an image sensor. So if you have a strip of image that needs to be captured, we use a small mirror at the top to deflect the light rays onto an image sensor which is at the bottom. Now all the mirrors corresponding to the different strips of the left eye view will fall along a conical surface in this design. And same holds for the right eye. Now if you combine the two views, you would notice that all the mirror strips for the left eye and the right eye in fact combines together to form a single cohesive shape. Moreover, we also prove in the paper that these mirror surfaces do not occlude each other. Now in the final design, we derive the shape of these surfaces which are not planar. In fact, we introduce curvatures to the surfaces both in the horizontal and vertical directions and derive the shapes required for both. In the rest of this video, we present panoramic stereo images of static and dynamic scenes. The results are presented as anaglyphic video, and first we show results of 4 different static scenes. Please use a red cyan anaglyphic glass to see the results. We now look at a dynamic scene where a set of dominoes are falling in cascade. Once again, please use an anaglyphic glass to see the results. Here is the scene as you would see it from a regular monocular camera. You notice that there are action happening at 2 different places in the scene. If you look at it using our camera, you notice that the dynamic scene is captured using a single camera. Once you de-warp the scene, you will get a panoramic stereo image of the whole scene. Once the scene is captured, you can focus our attention at any part of the scene. The 2 parts are showing 2 different sections of the scene.